This video is a continuation of the example of finding the magnetic vector potential for a spinning charge, a spinning spherical shell with a charge density on the surface of sigma. So where we left off in the previous video was we now have this integral which we have to solve, but now it's in a shape where it would be much easier to solve. And so when we do, the solution to this integral is v to the 3/2 power over 3/2 4r squared, capital R squared, minus r squared plus lowercase r squared, square root of v over 4 little r squared, big R squared times 1/2. And then both of those terms are evaluated from these limits right here. Okay, so let's plug all that in, and what do we get? We get square root of v over, well, we'll kind of, sorry, let me factor this out first. Okay, now it's a little cleaner. Okay, like this. Okay, so now we can plug it in, which will be the square root of r squared plus lowercase r minus 2 rr times r squared plus lower r squared minus 2r capital R minus 3r squared minus 3 lowercase r squared, all of that over a 3. So that's the first term, minus the square root of r squared plus lowercase r squared plus 2 lower r big R, r squared plus 2r r minus 3r squared minus 3 lowercase r squared, all over a 3 again. And then I can't forget in the front that there's a 1 over 2 little r squared, big R squared. So it's getting really kind of messy. Okay, but now we can kind of start eliminating terms, and what we have is 1 over 6 little r squared, big R squared, square root of r minus r quantity squared, minus 2 capital R squared, minus 2 lower r squared, minus 2r r, minus the square root of the sum of those r's, quantity squared, minus 2 capital R squared minus 2 lower r squared plus 2r r. So you notice I took the 3 out and factored out and made the factor of 6 out front. Okay, so now when we put those all together, what do we have? We have 1 over 3 little r squared, big R squared, times the quantity minus the absolute value of the difference in the r's, times r squared plus little r squared plus r plus the sum of the r's, r squared plus little r squared minus r. So again, I factored a 2 out of both of those parenthesis terms above. Okay, and okay, and then so what I have is the vector potential is equal to minus a bunch of constants to times this integral that we are trying to solve. Okay, so let's work out the cases of, say, inside the shell and outside the shell. So inside, what we have is, so basically little r is less than big R, then this integral, basically plugging in the values for those in what we found up here. So we are basically taking the case of when lowercase r is less than uppercase r, and when that's true, then this integral, which is getting really kind of big to carry around, is equal to minus 2r3 over r squared. So that makes my magnetic potential equal to mu 0 sigma r omega little r sine of psi over 3 y hat, basically in the y direction. Or, since I have omega r times sine psi, that's just the cross product. So I have mu 0 sigma r omega crossed into little r divided by 3. If I'm now outside of this, so little r is bigger than capital R, then the integral becomes minus 2 capital R over 3 little r squared. And when I plug that in, what I get for the potential is mu 0 sigma r to the 4th omega sine psi in the y direction divided by 3 r squared. Which I now can, if I want to now write it as a cross product, I have to put an r in both the numerator and the denominator. So then that would give me mu 0 sigma capital R to the 4th omega crossed into r over 3r cubed. So we now have the two forms, the solution for our magnetic potential, outside and inside, and both of them are proportional to the angular velocity crossed into the distance r. So let's say I want to write this now in spherical coordinates. So we want to put it in basically in r, theta, and phi. And so in that case, what we would have is a mu 0 r omega sigma r sine theta in the phi direction divided by 3. So basically replace the y hat with r sine, I replaced it with the sine theta phi hat. So that's at inside. On the outside, it would be mu 0 r to the 4th omega sigma sine theta over r squared. That's over 3, also in the phi direction. And that's outside of the spherical shell. Okay, So that was the magnetic potentials. What about the magnetic field? So to get the magnetic field, I would now have to take the curl of the magnetic potential, which would be, in spherical coordinates, 1 over r sine theta d theta sine theta, the phi component of A, minus d the theta component of A, and then derivative with respect to phi. So that's in the r direction, plus 1 over r, 1 over sine theta d-ar d phi, minus d-dr r a in the phi direction. So that's the theta direction, plus 1 over r d-dr r a theta component, minus d of a, the r component, the derivative with respect to theta, and that's in the phi direction. So what we have is we have a potential which is only in the phi direction. So that means a sub r is 0, a theta is 0. So that reduces the problem then to 1 over r sine theta, the derivative with respect to theta of sine squared theta mu 0 r omega sigma little r over 3 in the r direction, plus 1 over r, 1 over sine theta times the 0, minus d dr r squared mu 0 capital R omega sigma sine theta over 3 in the theta direction, which gives me 2 sine theta cosine theta over sine theta mu 0 r omega sigma in the r direction, minus 2 mu 0 r omega sigma sine theta in the theta direction, or if I clean up some more, 2/3 mu 0 r omega sigma cosine in the r direction minus cosine theta in the r direction, sine theta in the theta direction, which if you do the transformation is only in the z direction. So 2/3 mu 0 r omega sigma in the z direction. So inside this spherical shell, the magnetic field is uniform, is basically uniform straight field lines in the z direction. So in the end, what we would have is a spinning sphere where the magnetic field lines are now all pointing, let's say, in the z direction, and then outside they would curl back around to form something like this, which, if you think about it, is, kind of what goes on with the Earth. Except for it's a little bit different. Where there we have the current, the moving charge is now in the volume and not on the surface. But it's interesting that we can make this nice constant magnetic field inside the spherical shell